So in the last lecture, I introduced the model of billiard ball computing. This is a completely classical model, and it gives a physical construction of the mathematical framework. It's idealized, but that is fine. That doesn't cause any problems, and all that is used is just Newton's law of classical mechanics, elastic collisions, nothing more than that. So let us just rewrite the components of this. So the movement on diagonal grid, collisions are elastic and two-body processes. Then the reflectors are either horizontal or vertical. And the mapping is 0 or 1 is interpreted as absence, presence of a ball on that particular grid, and it runs at a uniform speed. No energy input at any stage or dissipation either. And the simple thing which I mentioned is what happened in the two-body collision. So this is a picture . And you input two variables x and y. So this will come out if x is equal to 1 and y is equal to also, no, x equal to 0. This has to be absent. So it's x bar and y. This will go through if y is absent, so this is equal to x y bar, and the other thing will happen only if both of these are equal to 1, so this is xy and this is also xy. So it basically generates the ingredients needed for the logical AND operation. Now, I had mentioned earlier while discussing the permutation representation of this Boolean algebra that if you look at the truth table, every input variable occurs an even number of times. And if you look at operation like AND and OR, the number is odd for the output. So that was all that was possible with two-body processes. How did we get around it? And this is another trick or observation. which is valid in this particular model, that we got around it because the variable appeared twice. So 2 times an odd number is an even number, and you can generate it using various kind of permutations. And this is a feature which will appear in various disguises, that this billiard board model produces some of the outputs twice. And that is a consequence of the conservation law, that the number of inputs, or rather the possible input states, have every variable with 0 and 1 occurring even number of times, so somehow you have to maintain that in the output. So now let us construct one of the universal logic gates from this particular process, and the easiest one to construct is the so-called switch gate. Which was defined as x and y go to one of the variables remains unchanged, but the other one goes into 2 possible locations, and you can label them in some way. So if x equal to 0, let it remain unchanged, and if x is equal to 1, it shifts to the 3rd position. Okay, it's a 2 input, 3 output particular process, and there is nothing wrong in the reversible nature, because from this output you can recover y by adding these 2 results. They cannot be simultaneously 1. So you can bring back from this state to xy if you want. Okay. And it has the ingredient that the AND operation is buried inside here. So you can use it in some particular way. So how do you produce it? With this particular ingredient, and I will give the result first before describing what happens. So it requires some amount of jugglery using this elastic collisions, and my drawing has to be more accurate, so the right angles look believable. These hashed lines are reflectors. You can insert as many as you want in this grid, depending on the operation that you want to perform. So let me see this, let me be x, and this is y. If y is not there, this is supposed to go through. So this is equal to x, y bar. This will go through in this direction if x is not there. So this is x bar y. But something else happens if both of them are simultaneously present. If both x and y equal to 0, everything will be 0 on the outside. So nothing is going to come out if you don't throw any balls on the other side. That is fine. So what happens when x is equal to y? That these two will collide first. Then this will be directed this way and this will be directed that way, and I put a reflector over here, so whatever is directed is now going in this position, and whatever is directed is now going in that position. So if I, let me see, x came in, y came in, then x, y will end up over here, and the point is that there has to be a second collision if both x and y are present, so they collide once at this particular point. This will come here and this will come here, and it has an equal path length, so it will direct in this particular position, and they will collide again. Okay. So after the second collision, this will go in this particular direction, while the one down will go in this direction. So this is actually whatever directly came in addition to this, it got added, and this one came with xy, and it ended up in this particular direction. Okay, so this is actually wrong. It got reflected by the second collision, and after that I'm drawing, yeah, I should not have drawn this body here, it's not necessary. The second collision takes place little differently, so let me draw the position. This is going to this way, this is this way. So when the collision occurs, this is the center point of contact, so it now the two paths have to be equal. Let me get the geometry right. It's on top of it in there. So it occurs here. That is fine, but the collision has to be in a position so the two paths are equal, they are moving at constant speed. So after the collision, this one lands up in this direction, and this one lands up in this direction. So the result is this, and this combination is x, y bar and y add up to 1. So we have produced this particular result, 2 input and 3 outputs. It all means perfectly timed in the sense that you count the length of this path, it is exactly equal to the length of that path, etc. and nothing goes wrong. So that solves the problem that yes, you needed this particular gate to be able to do Boolean logic completely, and you are able to construct it from this collisions. And remember, the duplication is always there. It's not achieved by one collision, you are using 2 collisions, and that is why all the permutation rules are well under control. So this is a simple example, but yes, you have to figure out how to play with it. It has everything as a subset. For example, if you want to produce, say, NOT gate, so I just put y equal to 1. And then this will produce the NOT gate, it is x bar. xy is the AND gate, and you can do various combinations of, you want to get, the opposite of this, you add these 2 things and it will become x times y plus 1, which is equal to y bar. So xy bar can also be produced. All kind of jugglery can be done. Okay. So nothing complicated is going on, but it's doing the job. Yeah.
Where is the duplication?
Duplication, there are 2 collisions.
Duplication means we are copying something, or we are making a copy.
Or you are using 2 operations, one after the other. It's not achieved by one operation. In sense, one operation will produce it, but there were 2 copies and you are rearranging them to recombine whatever the 2 copies.
State is recovered after 2 operations. Are you saying state will be recovered after 2 operations?
2 operations are needed in terms of 2 collisions which are in this circuit that produces the switch gate. Remember, switch gate had no conflict with the permutations. An even more interesting concept is a measurement. And the classical concept is that the measured state doesn't get affected at all, but the output will be 0 or 1 depending on the state which is measured. Again, you have to think about how this can be done, but the answer is something similar in the construction, that you can't do it with 1 collision, you have to use 2 collisions. So first collision will detect something and then you have to return the state to its initial scenario. So I have to cook up some structure that first I have to make a state which is present all the time. So I will construct a state by saying that in this grid box, some particle is going around. It's a closed cycle. It will remain there forever if you don't do anything, as long as the stuff is elastic. And so there is something in this trajectory, and you want to find out whether something is there or not. The point is that after you find out whatever the ball is running around, it should be in the same state, while the result will be different. So I will throw in a probe. From outside, and the job of the probe is to figure out whether something is present or absent. Okay. The absent part is quite trivial, that if nothing is going around the circle, it will just come out straight. But what happens if there is something present? So I will have to construct a collision. Okay. So let me again do the timing kind of perfectly. So this is a collision location, and it will collide on this line. Let me flip this arrow because I want to collide it this way. Doesn't matter. So the timing is all assumed that when they collide, they are in this particular location. What happens if they collide? That this will bounce in this direction, and this will bounce in this direction. That is not good enough because this got disturbed. I wanted it to return to its original position, so I will do something clever to put another reflector which brings back these two things together, and then there is a second collision which is here, and here. It has to be, this went this way, and this way, this went this way. These lengths have to be all equal, so fine, it is a perfect square. So over here, and this came back, and it will return. If there is a second collision, the result will be that it went around, it came back to its original circuit, this top one. The bottom one went around, but it landed over here due to the second collision. So if there was a ball going around in this circuit, the probe lands up here, moving this way, which is distinct than the first situation where the probe was here. So this is a measurement. If it's absence, the probe is here. If the presence, the probe is over here, they can be distinguished perfectly. While the whatever ball was running around the circuit, it has gone back to its original state. So what you have done, you have conserved energy, but the momentum of this fellow changed depending on the presence or the absence of the ball. And where did that change in momentum come from? It came from these collisions, the way we have arranged. And remember, to return this state to its original input, we had to use two collisions. The one collision will change the momenta, and you have to restore the momentum of the observed state to its original value, so you use another collision to get it back. So, what are collisions with reflectors? Produce momentum change.
So those arrows are direction of movement of balls. Those arrows are.
Yeah, arrows denote the movement of the balls. Yes.
So in the switch gate case, there are three balls. The bottom ball is moving along its bar by direction,
Yeah,
and the ball which is in between is moving along the dotted line.
yeah, but I drew the line dotted because it depends whether this one is absent or present. So they are all conditional results. And various things you can say. For example, this is an example of a merge operations. You have two different type of inputs, and as long as both of them are not equal to 1, you can add them together. And you can get some results like this. Remember, this is a classical scenario, though there is no constraint on either copying or merging. It's fine, they work. It's only the quantum circuits where you have to worry about no cloning type of constraints. Here, they don't appear. So this essentially gives a complete prescription of Boolean logic implemented with elastically colliding billiard balls. What we have not worried about is the complexity. How many of such collisions will be required to generate arbitrary algorithms? Well, it might look a little bit messy and you have to undergo lots of collisions, but it's an existence proof that it can be done. So optimization is a different story. Okay.
So the probe is also a part of the billiard ball.
No, it's a measuring instrument.
I mean, that also constitutes the billiard balls only.
It's a billiard ball only.
That also like goes on the grid.
It all goes on the same grid. But its system and apparatus are labeled differently, whatever it is.
We will say that every even number of collision will bring the system back to its same state.
Yeah.
And that is why we are saying that even number of variables, when the output results in even number of variables, it can be inverted.
Yeah. So that is a kind of generic feature in this particular model. Every model doesn't necessarily obey that kind of structure, but this is in some sense, what can be called a conservative model, in the sense that the number of balls is always constant. you can't either create a ball or destroy a ball. So if you want to create extra states, you have to duplicate. That is well, in some sense, the cost, additional cost in this particular model. But that doesn't matter. It's a kind of a fundamental demonstrations that thermodynamics plays no constraint on implementation of classical Boolean logic. Nothing is lost, nothing is created, energy is fully conserved, and the process takes place in finite amount of time. So there are, well, lots of statements in the older literature with respect to the second law of thermodynamics, what is allowed, what is not allowed, how quickly you can do such things, or whether there is a bound, etc. This example clarifies all of them in one go. That yeah, you don't have to worry about a whole lot of thermodynamical constraints.
These reflectors are placed additionally besides the boundaries.
Yeah, these are extra reflectors, as many as you want. You can insert it because you want to implement some gate. Gate needs some hardware, and these reflectors are doing the job of those hardware. There is an overall boundary outside, which is fine, that is a constraint, but you can add extra reflectors inside. So remember, the constraint of what happened to second law of thermodynamics is only in the sense of erasure. This will hold through, you get some result. Now you want to reuse the machine, you have to rearrange those balls and throw out all the information position. When you erase that position, well, you are putting in some cost. But until then, nothing. And the eraser cost is parameterized in terms of this free energy in thermodynamics, and that is a well, standard Boltzmann formula, that this is written in the physics units. Its kT is the standard constant which appears in counting the states according to Boltzmann rule, and how many states are there? Well, it is 2, because of the binary arithmetic we are using for bit. So if you erase one bit, the cost is kT log 2. That's it. Nothing more is needed. Now you can ask how are you going to implement various things, and I can write down very simple circuits to do various things. So examples of I will give a couple of them. The one of them is the standard component of elementary Boolean operation, which is called an adder. What happens when you want to add 2 bits? So it requires 2 input and the possibility that a carry can happen. So carry is actually the easiest thing to calculate, and that is this control square not operation. It adds 1 to whatever the carry bit may be there. So this is essentially added. How do I do the sum? And that also we saw it is available through this exclusive OR operation. So in this simple notation, you need one of this control NOT gate and one of them this control square NOT gate, and you have performed the standard operation of adding 2 bits. Multiplying is kind of trivial because this first gate itself does the job of multiplying. You have to put this initial bit equal to 0, but it will multiply the 2 bits. So that is one of the simplest possibility. How will you calculate arbitrary functions? Well, they can be denoted by this multivariable polynomial in some particular sense, but you can compress all that to a very simple description, which is reversible, that you just use a extra control NOT operation to add the whatever computed function is to an ancilla bit. And why is it reversible? Because if you do it twice, this Boolean logic will remove this extra f of x, so you'll get back to where you came from. This is its own inverse. So these are simple constructions, but it says that you can compute anything with this reversible logic framework. You are not trying to optimize everything rigorously, but it's good enough to give an existence proof, and we give an upper bound. What is the overall construction? That if you had some machine M, the reversible stuff required only 2 executions, one with M and another with M inverse, and whatever output is there, it's copied onto this extra ancilla bits. So that is the additional space which is required. There can be arbitrary scratch variables in the work area, but they will all be returned to that original state, as I described in the last lecture. So this basically completes everything, and you can construct some specific problem. You can make up this kind of logic gates which will solve the problem. Not too complicated. And now I can also repeat what I said about quantum generalization. All you need to do is use reversible logic states as basis, add the extra feature, which is superposition. And this is possible because the circuits which you are using are all linear. The superposition is allowed. This permutation is one particular type of a linear operation. And then you can do the same computation with arbitrary input states which are allowed by superposition. And here there are various things which I have mentioned before, but I can write it again. So if you have say n bits which are now generalized to qubits, I can perform this superposition by rotating each bit by 45 degrees. It is not the flip operation. Flip operation will take 0 to 1 all the way. So instead of rotating it all the way, I am rotating half the way. That is what the superposition will allow you to do. And this is equivalent to writing how to put a normalization constant. That is this root 2 in the denominator. Every component 0 and 1, some order will appear once, whatever the string is. All the 2 raised to n components are buried inside here. And they all have equal weight, which is equal to 2 raised to minus n by 2. So, well, I can be more explicit. What is I? This is first bit, second bit. It's in the tensor product. So what has been buried in rather simple manner here, that n operations can superpose 2 raised to n components. This number is exponential in the number of bits. And that is the advantage which is available. Whether you are able to use it effectively or not, that depends on what happens at the other end. This is the input. But it allows basically a huge parallel processing. If you have a circuit with the superposition, you apply it to this particular state, it will process 2 raised to n inputs simultaneously.
So this doesn't present the addition of superposition into the system.
This, it's a rotation. So that is a n operations. I can rotate this qubit from 0 to 0 plus 1 by root 2 by a very simple operation. Each individual qubit is rotated separately. Hadamard gate is, yeah, that's the name for it.
So
I have not introduced yet the quantum gates, but that is what the name will be, yeah.
Here, middle term and last term are same, or the third operation is again applied.
Equal. So what happens at the other end? You run this whole algorithm and quantum bits will come out, because that is the space you are working with. After going through the whole circuit, this is the input, the output will be n quantum bits. So even though it has huge number of components, that output can measure only an binary result. And if your problem is such that the answer is contained in this n binary results, then you have a very good algorithm. If you can't do it, then you have not gained any significant advantage. And that is the crux of the matter in all the quantum computation business. Superposing 2 raised to n components is easy, but figuring out how to reduce this superposition to n observables, that is a difficult task. And it's very much problem dependent. You can't just do it for any arbitrary problem. Do the superposition, you can do it for any arbitrary problem. It's output which is constraining, for which case you will have a good algorithm, for which case you don't have a good algorithm. Okay. There is one particular caveat which I had not mentioned earlier, but I should mention it at some stage, that in complexity analysis requires and this is a implicit but a necessary assumption, and it is required because you write the complexity analysis as a function of the size of the input, and you are going to vary it. So are you going to design a new algorithm for every possible size of the input? No. You want to have something like a induction procedure, that if you know the algorithm for n input, for n plus 1, you can construct it from it. And this is an implicit assumption. It is sometimes called uniform nature of these circuits. So you have a procedure to construct the algorithm for any size of the input, and the reason this is assumed that the possibility which needs to be ruled out, that the answer cannot be hidden in if I only want to have an answer for a specific size of the input, I can cook up something where the answer is already hidden in the design. And if that is so, then I'm not solving the problem. I have to rule out that particular possibility, and this kind of iterative or induction mechanism says that yes, the answer is not hidden in the circuit because I can just extend the circuit from n to n plus 1. I'm not doing a new design all over again. So this is a important assumption, but all the circuits which we'll deal with will obey this particular property. When I'm saying that the problem is defined on n input, I will give a construction and it's easy to see what will happen for n plus 1. The answer is not hidden in the design, it is just a simple inductive procedure.
That means our solution will become machine independent.
Yeah, the solution is machine independent. Yes. Okay, so now I can go back to describing the kind of quantum operations which will simplify this reversible framework in some sense, and that simplification is the important part of optimization. Okay, you are reducing the resources for doing the same particular job. And so now I have to ask, what are the simplification possible? And for that I have to start describing the quantum operations which I gave in some sense earlier in the course in this particular language. Okay. So the permutation group of reversible logic is a subgroup of so because it's a subgroup, it's guaranteed that you can't do anything worse. You can't find anything better, you just stick with the subgroup. But because there are other possibilities, you try to find out some shortcut of doing the same job. You have a larger space in which things can happen. So we can now ask what we did for this reversible logic. I started with the permutation group, saying that 1-bit operation was there. There was a 2-bit operation of so many things were possible. that was not enough for Boolean logic. We went to 3-bit operations and listed it. Let us repeat it, this particular procedure, and now it will be, instead of a permutation group, unitary group involving 1 qubit, 2 qubit, etc. And we did that in the at least in the 1 qubit case very explicitly by describing what happens in a single qubit transformation. It was represented on the block sphere by just some rotation. That's all there was allowed, nothing more complicated can occur. So 1 qubit case is a rotation on the block sphere, and it can be represented as a 2x2 matrix on the state 0 and 1. So I want to write it in a particular convention. Okay. This is the description of what is described as rotation on the sphere, that there is an overall phase and then there is an axis of rotation which is denoted by this particular unit vector, and this is the angle of rotation. So this is a generic description, but it's convenient to write it in this what is known as a Euler angle decomposition form. Okay. And this is general theorem which was described by Euler in the context of rotation of three-dimensional space. What it does is removes this arbitrary rotation axis and replaces it by rotations along fixed axis. So rotation is either along the z-axis or along y-axis by the angle which is beta and gamma. This is another rotation along z-axis. And the point is it can construct any arbitrary rotation, and all you have to deal with in demonstrating that is multiply these matrices and write down the full form, and you will see that will describe the most general 2x2 unitary matrix in some particular form. And I will stick to this convention, and I have to get the sign correct. And if you remember, these SU2 rotations are all half angles which were present. So the magnitudes which appear are related to this angle gamma. And in unitary matrices, they can be written as cosine and sine functions because the square of them had to add up to 1. And then there are phases which depend on this z rotations, and they are well taken so that the determinant is equal to +1. So this is e raised to minus I beta plus delta by 2. This is its complex conjugate. And the other ones are the differences of the two angles. There's a minus sign here, there's a minus sign there. So there are arbitrary phases, and I can choose them to be beta plus delta, which is one value, and beta minus delta, which is another value. They are independent, and rearrange in this particular fashion. So the result is that I have a most general unitary 2 by 2 matrix, which I had described in a different notation earlier. But the point is that I needed only 2 magnitudes and 2 phases, and they are all written here in some particular manner. And this Euler angle description is convenient because now when you talk about performing the rotations, the axis choice is simplified. It's convenient when you try to put it in a hardware. You are not going to keep on looking for new axis for performing rotation. The rotation is about some fixed axis. The only thing is amount of rotation described by the angle, which can be adjusted by the strength of some external field. But it simplifies a control structure. So this is a most general 1 qubit operation available, and a special situation is this gate which was mentioned a little bit earlier, is so-called Hadamard gate, and it's a particular arrangement of these magnitudes. So this cosine and sine are both equal to 1 over root 2. It's a 45-degree rotation, and the numbers are rearranged to produce these particular values. There is, well, you can put in some value, including 1 for alpha, to arrive at this particular choice. But the only constraint which was needed for unitarity is one is the normalization, the other is orthogonality, and they are both very easily satisfied. And this is the gate which is used to produce this particular result from the initial zero state. It's a particular amount of rotation by a specific choice of angle. There is another important label which will be useful sometime in discussion of the algorithm, that this is also the It is exactly the Fourier transform operation on a 1 qubit space. It's a discrete version of Fourier transform, and we'll come to it when the explicit definition comes. But it has a lot of connection with physical interpretation, that what does this job of jumping between different bases do. It's analogous to changing the quantum coordinate from one representation to its conjugate representation. That's all the Hadamard transform does. And some operations are easy in the original coordinate, some may be easier in the conjugate coordinate. So you can exploit that particular structure. I just wanted to point it out at this particular stage because it's an important property and it is useful. Okay. So now I generalize this 1 qubit operation, and I can proceed. What happens when I go to 2 qubit case, and general transformation is a 4x4 unitary matrix. And well, I can parameterize that in some complicated way and figure out what is the good way to implement it. But there is a surprising answer, is that you don't need all that full generalization. If you want to implement arbitrary operations, you can again look for some simplification, that instead of writing a full matrix, some particular components are enough to make up by the full transformation with some sequence. And the surprising answer in this particular case is enough to use the control NOT gate, which was already there in the reversible logic. You don't need anything more. That's a tremendous simplification, because here there were lots of angles. Here just one particular choice is there. It will do your job. Combining it with, of course, arbitrary one. And one can use all kind of group theory details to demonstrate it. It's nothing against the principle, but probably giving rather simple examples is an easy demonstration that yes, existence proof is all you need. And I will give the example explicitly. Suppose I control U operation. Which can be denoted between notation for the reversible circuit by this kind of a diagram. What it means is, if the control state is 0, don't do anything. If it is 1, then apply this rotation. How can we construct it? Well, suppose you can find a decomposition, okay? So that some particular combination together will control naught, will do this particular job. So the decomposition looks like this. There is a 1 qubit gate combined with three rotations and 2 control knots. Okay. So what will this circuit produce? This gives the result that control equal to 0. It will give A, B, C, because nothing will perform this control knot with the 0 control. What you will have is a product of whatever this ABC is, and you don't want nothing to happen. So I want this equal to identity. Okay, so, and if control is equal to 1, then I have A times the NOT operation, which in this polymetrics language is sigma x. And that all get acted over here. So A sigma x, B sigma x, C, and I want to match this with this control U, which was the target. So to realize this particular circuit, I need to solve these equations. If I can solve it, then I can implement this operation in this decomposed manner. Okay. And the solution can be explicitly constructed. And that is the answer. I have taken this Euler angle notation and just explicitly wrote down the various factors. So you can easily see that if you multiply these things together, these factors of beta and gamma and delta are such that everything cancels. Because what will happen when you multiply A with B, this will drop out. Then all this remains are rotations of RZ. They are rotation about the same axis. So you can just add all the angles and they add up to 0. What happens when the control net acts? Then there is this polymetric sigma x, and it anticommutes with both y and z. So what can be done? I can use the commutation rule to take this sigma x through this b and sigma x square equal to 1. So it will cancel out. But in between is this operator b. And it anticommutes with both sigma y and sigma z. So the rotation operator, the angle flips sign. That is a consequence of anticommutation, because rotation operator is just given by the exponential of the polymetrics, and if the anticommutation is there, the angle of rotation flips sign, it is in the exponent, and so this will become plus gamma by 2 and this will become plus delta plus beta by 2. And now multiply the three things together. So there is RZ beta. These two together, this line has flipped, so it will become RY gamma. And these two together, the sign has flipped, it will become RZ delta, which is what this decomposition was.
We will get that thing. We will get that thing.
Yeah, this description, which is an arbitrary value for u. So, yes, you have to juggle around with algebra a little bit, but this is a demonstration that to carry out 2 qubit operations, just including this control knot in the list is enough. That is a tremendous simplification, because 1 qubit was implemented by a rotation of a single degree of freedom. 2 qubit you need to have an interaction, and you are saying that only some particular interaction is enough. I don't want arbitrarily complicated interaction. Don't have to worry about it. So this and one can now ask, well, do I need to go any further to the 3-bit operation? The answer to that also happens to be no. because of similar tricks, that arbitrary 3-qubit operations can be decomposed in terms of 2-qubit operations, and the 2-qubit operations can all be decomposed into this, and none of the 3-component operations are needed. Again, instead of a general proof, writing down examples is a quicker choice, and I will do that in a schematic form again. The similar trick. And the example I will take is a similar structure, which is the so-called Toffoli gate kind of generalization. Which can be demonstrated in that logic notation as can I find a decomposition of this? And again, there is a circuit which will do the job, and best thing is to just write it down again using control naught, etc. And 3 boxes will appear here again. The 3 boxes are U, U dagger, and U. So the U dagger is again doing a job, something like the sign flip, which is over here. It is the opposite. So things have to be cancelled in some particular manner, and oh yeah, I have to put a caveat here that whatever is there is actually square root of whatever matrix here, but that is fine. Unitary matrix, I can take a square root. So what is the trick here? Well, I have to again give a construction, and it will require only control naught and operations of this particular type.
Just one, there is a half periphery.
Half?
What is that symbol? Half periphery of circle. First one, above first U.
Because it jumps over this line. It has no connection to that line. Okay. So now let us ask what happens. Suppose the top control one is 0. Okay, then none of this in between stuff is going to appear, and if the second one is 0, even this will not appear, but if second one is 1, then U dagger and U both will appear and cancel out. Okay, so the take when the first one is 0 is taken care of. Now look at what happens with the first one is equal to 1. Then these two things are going to flip. Okay. And now ask what will happen if the second one is 0, then even if this is flipped, U dagger and U are going to act in a kind of manner which will compensate it. So let's see this. This one is 1, so the U is going to act. But put this equal to 0. That 0 got flipped by this to 1, so U dagger will act and it will cancel, and then it will again flip back to 0. This is not going to act. So that is also U and U dagger are taking care of each other. The non-trivial part is when both of them are equal to 1. So when both of them equal, this U is going to act. This is going to become 0. So this is not going to act. And this will again act. So the operation you have is U square. So what do we have here? Here there are a single qubit U, U dagger U, and extra stuff is control naught. And we have done the 3-bit job with that system, so none of the more complicated stuff is needed. And these are very simple illustrations, but they are buried in all the quantum algorithms that because of this tremendous simplification, all the algorithms which will construct will have 1 qubit rotations and a control naught, nothing more. That is enough to cover everything which can be done with a full quantum logic. And you have simplified a whole lot of stuff in the process in terms of hardware requirement. 3-bit interactions are not needed at all, and only a particular version of 2-bit interaction is needed. The rest of it is all single bit rotation. Now there are further constraints which I will describe next time, that yes, this is done with a bunch of variables. There are some angles of this type and that type. In practice, you need to digitize them. The angles are real variables. You are not going to work with a full real number possibility, although you can if you want. But sometimes it is useful to digitize them. And one can then ask, can I do a digitization, and then what will be the size of the error? So digitization means truncation of the real value. And so something is discarded, and then you have to say that, yes, I took some finite number of digits, but then I have to ask how much is the error. And that's a separate analysis, but you need to demonstrate that, yes, you can digitize this particular framework while keeping the error under control in a certain sense. And that gives a full-fledged formalism that, yes, you can do all the operations, and also you can do digitization with a controlled set of error, because the problems, as I had labeled them interesting in the computational complexity language, are in the class of BQP, bounded error quantum polynomial problems. So We want the problems to remain polynomial in terms of resource requirements, but we also want to have the error which is bounded. And everything which we can do with various jugglery then qualifies as a good quantum algorithm. So I will stop here.